Swayam Prabha. Digital India. Educated India.
Hello everyone and welcome to this course on gas turbines and jet engines. So, today is lecture number 24, which is the fourth lecture of week 5. So, today we are going to discuss the performance characteristics of real gas turbines. Okay, we were discussing real gas turbines in the previous few classes. We have seen what are the differences with ideal gas turbines and how to incorporate those differences. Then we have analyzed a few problems and tried to find out the effect of these additional features and differences. Now, we will finish this part by considering how the performance parameters vary with the design parameters for these different cycles, for the important cycles out of this. Not all the cycles are equally important from practical perspective. So, we will discuss that also. So, concepts which will be covered are different types of gas turbine configurations. Okay. So, this also we have not yet discussed. So, there are multiple configurations of gas turbines. One of the examples we have seen in the previous numerical problem, where we had considered a 2 spool system. Okay. And the main part of this lecture today will be on performance characteristic and comparison of real gas turbines. Okay, so, let us come to the gas turbine configurations. So, typically there are from the number of shafts, there are 3 types of gas turbines. The first is known as single spool gas turbine. Single spool gas turbine consists of a single shaft, as you can see here. This is the shaft, and all the turbines and the compressor stages are mounted on the same shaft, and the load is also mounted. So, this is the load, which can be a generator or it can be some sort of mechanical load for running a mechanical device. Okay. Load is also mounted on the same shaft. So, this is the simplest form of the design, and in this cases the load can be either mounted on the cold side, which is the compressor side, or the load can be mounted on the hot side, which is the turbine side of the shaft, depending on the application. This is the simplest design, but there are some drawbacks. For example, if the number of stages is too large, if the compressor pressure ratio is too large, then we will have large number of compressor stages. Typically, in each stage of a compressor, the pressure ratio for axial compressor is around 1.5. So, now if the overall pressure ratio is say 20, then you can imagine that there will be a large number of stages. So, in that case, the density of air changes due to this considerable change in pressure. The density of air changes quite significantly in the compressor as well as in the turbines. So, as a result, in the lower stages of turbine, means towards the exhaust region, in the lower stages of the turbine, the density is very less, specific volume is very large, which results in or which requires a very large passage area for the flow to occur, which means that the turbine blades, as we will see later, turbine blades have to be very long. So, if all the turbine stages are mounted on the same shaft, the turbine blades also rotate at the same rotational speed. While this is fine for the smaller blades, for the longer blades, the centrifugal stresses become too large, and that can be a problem. So, we have to reduce the rotational speed, which will come at the cost of performance. So, in those cases where the compression ratio is large and we have a large system, so it is better to divide the system into a 2 spool system, as you can see here, 2 spool system which consists of 2 shafts. So, in the top diagram you can see that there is a inner shaft, this one is a inner shaft, and on the inner shaft the low pressure turbine. So, this is the low pressure turbine and the low pressure compressor are mounted. Okay. Low pressure turbine, low pressure compressor are mounted and the load is also mounted in this case. While a separate shaft is there which rotates over the shaft, inner shaft. So, this shaft connects the high pressure turbine and the high pressure compressor. So, this is the high pressure compressor and this is the high pressure turbine. So, the advantage of this system is that both the shafts can rotate at different rotational speeds. So, for this high pressure compressor and high pressure turbine, we can rotate at a much faster speed because the length of the blades here are much smaller. Okay, lengths of the blades later we will see correspond to approximately these are aligned like this. So, the vertical distance that you see here. Okay, so, the lengths of the blades are smaller as compared to the low pressure stage blades which will be very long. Okay, so, as a result they can rotate at higher speed, while for the so if they rotate at higher speed, the blade velocity, rotational velocity is high, so blade velocity also is high. So, changes also like more changes can be accommodated in a stage, more work output per stage will be the output. So, on the other hand, the inner shaft which has the low pressure turbine and compressor can be rotated at a lower speed such that the centrifugal stresses do not exceed the material limit and there is no problem with the continuous running of this type of turbine. Now, again there are two configurations within this two spool system. The top one which you see is where the load is coupled to the low pressure spool, but that low pressure spool also has the compressor and the turbine, low pressure compressor and the low pressure turbine. So, there is another type of system where all the compressor stages are coupled to the turbine in a single shaft. Okay. So, for example, this is shaft 1. So, here the purpose of the turbine is to just run the compressor and nothing else. Okay. So, all the compressor stages are run by the turbines mounted on this first shaft and there is a second shaft which is not coupled to any compressor. Okay. So, this is known as and it is only coupled to a turbine and the load that is required to run. This is known as free power turbine or free turbine, okay, because it is not coupled to any compressor. Whatever power is generated by this turbine is used for running the or used for running the generator or for running mechanical load. Okay. So, what happens is that the gas which comes out from the first turbine goes to the second turbine is mounted on a different shaft, can rotate at different speed, depends on the load requirement. So, another advantage of having two separate shafts like two spool design is that the load can be mounted on a shaft which rotates at a given speed. So, in some cases for example, for generators the rotational speed has to be fixed like 50 hertz or 60 hertz. So, 50 rotations per second because of the frequency that is needed for current generation. So, in those cases the other shaft is free to rotate at a different rotational speed. Okay. So, in this case the second turbine is fully used only for running the load. So, that is why it is known as a free power turbine. Now, there are some drawbacks of this system, that this is this will have more capital cost and this will be bulkier because of the additional components that are needed. Okay. Design is more complex also. For even larger turbines where we need very high efficiency and the compression ratio is very high. So, that number of stages required is very high. There can be also 3 spool designs, like 3 concentric shafts are there, where there can be again 2 types of cases. 2 shafts have, so one shaft has high pressure turbine with high pressure compressor, high pressure turbine with high pressure compressor. Then the second shaft will have the intermediate pressure turbine, okay, IPT intermediate pressure turbine with intermediate pressure compressor, and then there is low pressure compressor which is connected to the low pressure turbine, and the load is also connected on the same shaft. The other design is where there are two sets, the compressor stages are divided into two stages, means two parts, and they are run by two turbines on two different spools, and then the third turbine is mounted on a separate shaft and is free to just run the load. Okay. So, this again has advantages that the load is decoupled from the, so rotational speed of the load is decoupled from the overall rotational speed required for the compression and expansion processes. So, these are some of the main configurations of industrial gas turbines. Later in the next after a few classes we will start discussing jet engines. So, there we will see various types of configurations are present for jet engines also, because they have more number of devices and more say more variations in design. So, more different types of designs or more variety of designs are present. So, we will discuss those, but for industrial gas turbines these are the main designs, and solving a problem again remains similar to all the problems that we have solved previously. We just have to go step by step, find the temperature at each point. Okay, so, starting from the inlet, say for the example, then the temperature here, then the temperature in the at the next point, temperature at the next point, like this we go on, and then we can find the enthalpy changes. From that, the work input to the compressors, work output to the turbine. We can use the conditions necessary. For example, the HP turbine runs the HP compressor. So, work output from this turbine is equal to the work input to the HP compressor. So, similarly, we can use other conditions and we will get the final performance parameters. So, ultimately based on different design parameters we can generate different performance parameter values. Now, let us finish this part, okay, of industrial gas turbines, which we are studying from the beginning, by having a brief discussion on the performance of this real gas turbines. Okay. We have discussed the performance of ideal gas turbines, we will discuss the performance of real gas turbines now and how it deviates from ideal gas turbines, and then we will have a few brief comments on the comparison of these different types of gas turbines, okay, which are feasible, what is important from industrial perspective, things like that. So, for a simple gas turbine or for any of these systems, real systems, we cannot generate expressions like a mathematical closed form expressions for say relating the performance characteristics like efficiency and the net specific work output to the design parameters, because the number of design parameters here is so large that it is almost impossible to generate such a closed form equation. So, the way to find the performance characteristics here is to do design point calculations, say for example, with a given set of inlet condition, then pressure ratio, turbine inlet temperature, but apart from this given set of efficiency of the compressor, efficiency of the turbine, combustion efficiency. So, like this there are several parameters which we have discussed, regenerator effectiveness. Okay, so, to incorporate all these effects and then find the value of the efficiency and overall efficiency, thermal efficiency and specific fuel consumption, and then keeping on repeating these calculations in an automated form by writing a computer program, and by changing one variable at a time, by keeping on repeating these calculations we can generate graphs like what you see here. Okay, so, these are known as performance characteristic maps, and this gives us insight on the behavior of the compressor or the behavior of the compressor in terms of its performance based on different design parameters, important design parameters. So, you can see here that the first plot plots the compressor pressure ratio, effect of compressor pressure ratio on the cycle efficiency. Okay. For ideal cycle, we had discussed previously, if you remember, that the compressor pressure ratio affects the compressor pressure ratio is the only parameter for ideal Brayton cycle. It is the only parameter which affects the efficiency. Okay. There was no effect of the temperature change, so no other effects. So, in this case, in contrast to the ideal cycle, which is shown here by this dotted line, in contrast to that, the maximum temperature of the cycle or the temperature ratio plays an important part. Okay. As you can see, if the temperature is maximum temperature is less, so 1000 Kelvin, we get a significantly lower efficiency, and the efficiency keeps on decreasing after some time. Unlike the ideal cycle, where it was not decreasing at all, it just kept on increasing. Here it goes to a maximum value and keeps on decreasing. Then at a higher temperature, it increases further, but again it will start decreasing after some point. The maximum efficiency for a higher temperature occurs at a higher value of R or compressor ratio RC as compared to the lower temperature. So, optimum value of RC is different and higher for higher value of maximum temperature, turbine inlet temperature. Similarly, if we go to a even higher temperature, the peak value will be at a higher value of RC, further higher value of RC, and the peak value also will be higher than the previous cases. Okay. So, why this happens? This happens because unlike the ideal cycle, in these real cases there are losses in the compressor and the turbine. So, even some amount of temperature difference is needed, or some amount of heat addition in the combustion chamber is needed just for running the turbine and compressor, such that the turbine generates just enough work to run the compressor, no additional work output occurs. So, in that case the efficiency goes to 0 at that condition. Okay. So, let me explain again. So, here because we have losses in the turbine and the compressor stages. So, when we have a very small amount of heat addition in the combustion chamber, the work generated by the turbine is not sufficient to run the compressor. If we keep on adding more heat in the combustion chamber, then the work output from the turbine will increase, and at some point it will reach a state where it can run the compressor, but does not generate any additional work. So, if we keep on increasing the heat addition and go to a higher temperature in the combustion chamber from there, then we will get net positive work output, and as a result then we will get some positive efficiency and the efficiency will increase. Okay. So, that is what we see. On the other hand, if you go to very high value of compressor pressure ratio, we see that again the plot dips, means the efficiency decreases. So, at very high value of compressor pressure ratio, the losses in the compressor, the compression process is very long. So, the losses in the compressor also becomes very high. So, that creates, so that negates the effect of additional say work output that we would have. So, in that case again the efficiency decreases. So, these are only two important parameters. So, there can be several combinations, as I was saying, the effect of ambient temperature, effect of ambient pressure, effect of isentropic efficiencies of different components, regenerator effectiveness. So, like that we can have various factors which can influence the results. So, for each case, so it is not possible to show all the cases here comprehensively, and it is not needed also. We can always try to do design point calculations and come up with performance maps on our own for a particular set of parameters. So, just to again summarize this part, for the simple gas turbine, eta becomes a function of both the temperature ratio, as we can see here, with temperature it is changing, assuming that inlet temperature is fixed. So, both temperature ratio as well as compressor pressure ratio. Here we are explicitly denoting that the pressure ratio is compressor pressure ratio, because the turbine pressure ratio will be lower than the compressor pressure ratio because of pressure losses. Okay. Then the peak value of efficiency occurs at a particular value of RC. For example, for this case the peak value occurs somewhere here. Then maximum specific work output occurs at a lower value of RC. So, these are the maximum specific work output lines which we have not discussed yet. So, we also see that maximum specific work output is similar to the ideal cycle. However, these values will be lower slightly than the ideal cycle, not slightly, it will be considerably lower because of losses in the compressor and turbine as well as pressure losses in the combustion chamber. So, but their characteristics is similar in the sense that with increasing RC, the specific work output reaches a peak value and then again it starts decreasing. Okay. But the optimum value at which this maximum work output is obtained is at a lower value as compared to the optimum value for efficiency. So, for example, for 1000 Kelvin we see that the optimum value of efficiency is greater than 8, but the optimum value of work output is less than 6. This can be exactly calculated based on the plotting the graphs, but we are just approximately comparing them here. So, then also we know that with increasing temperature the specific work output will significantly increase, okay, because now the scope for expansion in the turbine is much higher and we get much higher work output. Very strong effect is there, which is much stronger as compared to the effect of on efficiency. Now, the other point is that performance curves are flat near the peak. Okay. So, particularly say at these intermediate temperatures we can see that performance curves are flat near the peak. Here also it is flat near the peak. Here the peak is not yet reached. So, near the peak it will become flat. By definition it has to be flat because then the efficiency again starts decreasing, means it need not be flat, there can be a sharp transition, but in general it is the case. Same occurs for the maximum work output. So, any value of RC between these two optimum values, say for example, any value between this 6 and 8 would be suitable for us and will not lead to significant loss in efficiency. Okay. So, based on this, typically the lowest acceptable pressure ratio is chosen. This has the advantage that it reduces the number of compressor and turbine stages, okay, and avoids the excessively small blades at the high pressure end of the compressor. So, first point is clear, reduces the number of compressor and turbine stages. If we have lower pressure ratio, we will need lower number of stages because the expansion and compression processes are smaller, and lowest acceptable pressure ratio is chosen, which means that within the range we should have near the optimum say work output pressure ratio, or if there are any limitations from practical point of view. The second point is that if the pressure ratio is too large, then the compressor the density, the specific volume keeps on decreasing significantly with increase in pressure. So, towards the higher pressure stages, or means the end of the high pressure stages, the specific volume is very small, specific volume of the compressed air. As a result, the passage area required for flow becomes very small, which creates excessively small blades at that end, which will have. So, then the ends of the blades actually influence the flow pattern, which can lead to inefficient flow through the compressor. Okay. So, that is one important point. And finally, the work output and efficiency increase with higher turbine inlet temperature, both increases as we have seen here. Okay. The optimum value of RC for both cases also increase with higher turbine inlet temperature, that also we have seen. So, going from here to here, okay, and somewhere around here. So, simple gas turbines are very widely used, designs based on simple gas turbines, because they are very effective and have very good performance and are simple to design, okay, with less capital cost. So, then we will have a quick discussion on regenerative gas turbines and some comments on the reheat and intercool cycle. Regenerative gas turbines are also used, means gas turbines with regeneration, although they are not as common as simple gas turbines. So, what are the features? So, we have shown here only the, I have shown here only the variation of efficiency versus RC. Again we can generate these plots using design point calculations. So, in this case for efficiency we see that the variation is completely different, okay, as compared to the ideal cycle. If you remember, for the ideal cycle, the efficiency was started at the highest value and then would decrease with increasing RC, something like that. Okay. So, this would decrease with increasing RC, and this is with higher temperature you get a higher value. In this case, however, here the efficiency becomes 0 at a certain value, where certain value of RC, this occurs where the RC is just sufficient to run the turbine and the compressor, means the entire turbine work is used up for running the compressor, there is no scope for any additional work output. So, efficiency becomes 0 here, and if we keep on adding heat, then we will have scope for more compression. So, more compression ratio can be there, which will release some net work and we will get a positive efficiency. Now, this efficiency increases sharply, unlike the previous case where the efficiency increases slowly. In this case the efficiency increases sharply and we reach a peak value at a much lower value of RC. So, here you can see it is less than 5 as compared to this case here, which is around 8. Okay. So, we reach a peak value which is at a much lower value of RC. Similarly, for temperature 1200 Kelvin we get something like this, then 1500 Kelvin we get something like this. Diagrams may not be accurate, but you get the qualitative picture. Here 1200 Kelvin will be much higher, 1500 Kelvin is even much higher. Okay. So, the optimum value shift towards the left, and the regenerator effectiveness also plays an important role. Okay. So, the points that we can note here are that efficiency versus compressor pressure ratio curves are completely different from the ideal regenerative cycle. Here there is a minimum value of 0, then it increases to a peak value and then starts decreasing more or less sharply. Efficiency is 0 at not on RC equal to 1, but it should be at a value of RC where the it goes to 0 even before RC is equal to 1, means at a value of RC where the turbine is just sufficient to run the, generates just sufficient work to run the compressor. Peak value of efficiency is higher than simple gas turbine and occurs at a lower value. So, peak value for example, for 1000 Kelvin will be higher than the peak value here, which is some 22-23%, here it may be 26-27%. Okay. So, peak value is higher than simple gas turbines. Specific work output, although we have not shown here because its behavior is exactly similar to the simple gas turbine. The only difference is that because of pressure losses in the regenerator, the work output gets slightly decreased. So, the work output will be like this, okay. This will be T03. So, it will be slightly lower than the simple Brayton cycle. Remember that for ideal cycle it was exactly same as simple Brayton cycle, ideal cycle. Here it is slightly lower than the simple Brayton cycle, and this is only because of the losses, pressure losses in the regenerator. And increase in regenerator effectiveness. So, you can see in the top plot. Okay. So, this dotted line is for a regenerator effectiveness of 0.625 for 1500 Kelvin. This solid line at the middle is for 1500 Kelvin, but regenerator effectiveness of 0.75. Okay. And the top line is again 1500 Kelvin, but regenerator effectiveness of 0.875. We can see that there is significant increase. So, the regenerator effectiveness plays a major role in determining the efficiency of the cycle. Then we will have a few comments related to the reheat cycle and the intercooled cycle. These are not as widely used, reheat and intercool cycle. So, we are not going to plot the performance characteristics, you can of course generate performance characteristics. So, reheat cycle independently is not very useful. Similarly, intercool cycle also independently is not very useful. We have seen that from the ideal cycle analysis itself, that when only reheat is added, the specific work output increases, but the efficiency decreases. So, it comes at the cost of efficiency. Same thing happens for intercool cycle. So, we do not want to just add only reheat or only intercool or reheat and intercooling. We want to add reheat when it is all means going to be coupled with regeneration. So, reheat can only make sense if it is coupled with regeneration. Then we do not have the efficiency loss and we get higher work output also. So, reheat improves the specific work output, higher pressure loss results in lower efficiency. Okay. So, in reheat cycle in general the efficiency is lower, then more pressure loss will occur, even lower efficiency will be there. Then there are practical problems which are related to high specific volumes at the lowest pressure turbine stages. This leads to excessively long lower stage turbine blades. What do we mean by that? So, if you quickly consider the reheat cycle, okay, let us say that we have this compression process and then the first heat addition, then first expansion, high pressure expansion, second heat addition and the second expansion. Okay. So, 03 to 04 is the first expansion, 05 to 06 is the second expansion, 04 to 05 is the reheat. So, from 5 to 6, so compared to 3, the pressure at 0.5 is significantly lower, the reheat pressure is significantly lower than the primary combustion chamber pressure, but the temperature are same, which means that the specific volume here is much higher, density is lower, which means that after expansion the final specific volume is going to be very high. It is much higher as compared to a case where if no reheat was used, the specific volume would have been much lower, temperature would have been lower, specific volume would have been lower. So, this increase in specific volume leads to or requires more passage area for the flow to occur, which means that turbine blades needs to be longer. Okay. So, that is one of the main drawbacks. So, and as I was saying, using reheat only makes sense when combined with regeneration. Now, for intercooling, the behavior is similar to reheat. So, we are not going to repeat that part. Behavior is less excessive, means the loss in efficiency is lesser, but the gain in the work output is also less, and intercooling makes a lot of sense when combined with regeneration. They are very powerful with regeneration. Okay. So, performance is similar to reheat qualitatively, but we face less problems as compared to reheat, unless you consider the means for fixed gas turbines with fixed locations we face less problems, but it makes the system very bulky. And another major drawback is that the self contained nature of the gas turbine is lost. Now, the gas turbine depends on this external water supply which is needed for running the heat exchanger, okay, or the intercooler. So, the self contained nature is lost. So, you are dependent now on your surrounding supply. Okay. So, to summarize this part, although these are all important say concepts and have been widely used previously, in modern turbines to get high efficiency either simple cycles with high value of RC is used, okay, and accordingly the means optimum RC is chosen for high efficiency and work output, or low RC, low value of RC near the optimum case for regenerative cycles are used. Okay. And only a few cases are there where regeneration is combined with reheat or regeneration is combined with intercooling. If you have a very large system and efficiency and work output plays a very important role, then in those cases combining all these different say different types of variations makes sense. So, we will conclude this class. So, in this class we have analyzed the performance characteristics of real gas turbines. We have also seen different configurations of the gas turbines, and then we have had a few comments on the various types of industrial gas turbines. Okay. So, from the next class onward, we will have a very quick, in the next few classes we will have a very quick summary of or overview of the different components of a gas turbine and jet engine. Okay, we have finished this part on industrial gas turbines. So, we will go through components component wise quickly, and then in the second part of the course, major second part of the course, we will start with jet engines. Okay. So, these are the references. Thank you.